Hi, thanks for joining me today at SC25 in St. Louis. My name is Vivek Kale. I'm a principal member of technical staff at the U.S. Department of Energy's Sandia National Laboratories. Today, I'm going to be talking to you about work I've done in the last few years in the direction of auto-tuning and performance optimization for OpenMP GPU programs using AI. I will particularly discuss my recent pathfinding work and my future work in this direction. To understand why we need AI/ML for OpenMP performance tuning for our simulations today, it's important to first take a big step back for a moment and think about first principles. Scientific simulations run on a supercomputer have this following skeleton structure with a local operation often comprised of a standard for loop with an enclosing computational operation. This local operation is surrounded by a time-stepping loop, and this is often called an outer iteration. Now, for parallel computation across distributed memory machines, this local operation is preceded and succeeded by a process level communication, most often in the form of MPI. The challenge here is that simulations run on a supercomputer fundamentally must run across all nodes of a supercomputer in a scalable fashion. MPI has been heavily optimized over the years for point-to-point and collective communication. If we run this problem size on, say, 100 per process and 1,000 time steps, it should scale to any number of processes given an efficient MPI implementation. The reality is that it doesn't, no matter how efficient and optimized the MPI implementation is. Given the advent of GPUs and node-level heterogeneity on supercomputers, nodes have become fatter and more complex, which includes transient or probabilistic system perturbances. Now, if we look at the application timeline here on the top left, where light blue boxes indicate MPI processes, dark red rectangles indicate the core's computation within each MPI process, and the dark blue is its performance perturbance, or noise for short, and let's say that it's 5 milliseconds. Now, given each time step is 10 milliseconds, and the probability of noise on any node is 1%, the expected time with the noise is 10.05 seconds. This isn't much of a delay. But now, if we increase the program to run on 1,000 nodes, which is not an unrealistic number for a simulation, the expected time with noise is 14.449 seconds. That's around 50% slower. This is the noise amplification problem. And you can model this here further through this chart that I have, and you can see this inflection point as you go up to 400 processes. This was actually first in simulation, done through simulation in SC10 by Torsten Höfler, and then I've later on done some of my own mathematical and performance modeling of this, and you can see more information here. And this problem actually maps to a more general and open CS problem called weight-free consensus. No solution exists to this problem, but we can have approximate solutions come close to an ideal answer. So, how do we solve the problem in the context of science simulations? At the bottom, we see one approach of redistributing work across the cores of a node, and this effectively paralyzes this perturbance or noise across those cores. But we have to be mindful that the redistribution itself has a cost to execution time. So given many applications use MPI plus OpenMP, it really falls on OpenMP to handle this kind of work redistribution and optimization. This means that efficient and performance variable OpenMP can prohibit MPI scalability. This is a key and underlying reason why optimizing OpenMP is so critical to our exascale supercomputers. The thing I intend to point out here is that AIML benefits for finding the best performing OpenMP strategy that will help MPI scale. Now, let me first point to prior work I've done to help exactly the noise amplification problem, where I've applied OpenMP performance optimizations to a CALU factorization on nodes having multi-cores and GPUs. Here, I show this application timeline diagram of the CALU, with this top diagram showing the static schedule. And you can see these white pockets of idle time. The second diagram shows dynamic scheduling applied to CALU with the best performing chunk size. And this doesn't have many white spots, but has a lot of red spots showing DQ overhead. A basic improvement over both the static and dynamic scheduling is to use a mixed static dynamic schedule via this new OpenMP schedule shown here. This gets the best of both and identifies the trade-off between work redistribution and the cost it incurs. In this strategy, we run some number of iterations that are pre-assigned, and then each thread obtains iterations dynamically and runs those iterations. The number of iterations each thread executes is this dynamic fraction. And this converse of that is a static fraction. We can tune this parameter. And by doing this for CALU, we improve performance by 30% over the static schedule. And we also got better performance consistency. This also beats the deep plasma LU factorization by 40%. And I am working with the Slate team to improve LU factorization in this library via this approach. But we can also create a cost model for this, given the search space for finding the best static fraction is large. In this work shown, I developed a cost model that bounds the static fraction by the following formula, given prior information on the expected noise duration in a time step and the length of the time step. Thinking about MPI plus OpenMP, this model tells us that more nodes means the best performing static fraction is lower, and we effectively need to do a larger percent of dynamic scheduling. To consider impact of MPI communication blocking time, this fraction will need to be adjusted per MPI process. Now, coming back to AIML, the critical question here is, what's the best strategy? And what are the right parameters for an application platform pair? This is a complex problem, as you can see, but it can be learned or machine learned across applications and different platform pairs. And let's see what we have already done here in the context of AI/ML. We set a goal for the machine learning of an optimal OpenMP loop that satisfies two or multiple objectives. Both the objective of data locality via minimizing coherence cache misses and the objective of load balancing via minimizing thread idle time. To get there, we generated a new OpenMP loop from the original OpenMP statically scheduled loop and OpenMP dynamically scheduled loop. That generated OpenMP loop specifically tries to define a point of control within that OpenMP loop through which a sweet spot of a performance trade-off or solution to the multi-objective tuning problem can be easily found. Automating this discovery and generation of such new schedules is essentially a token generation problem. Token generation plays a crucial role for generative adversarial networks, or GANs. GANs are behind a large amount of recent research in generative AI and actually very relevant to ChatGPT. Now, once we define this generated OpenMP loop schedule with the control point, we adjusted this control point. We did that by defining a knob or parameter, specifically the static fraction, and then tuning that knob to find and learn the sweet spot or optimal parameter value that is best performing for an application architecture pair. We also used a performance model or cost model for training to guide finding the sweet spot given prior knowledge. Here, the prior knowledge was the perturbance length and duration of a time step. Automating this kind of tuning and learning of parameters is associated with Bayesian statistical model optimization, which is already an active area of research in the DOE in the context of Clang LLVM loop optimizations. Now, to globally find the best solution, we essentially had to search amongst the different tuned versions of each OpenMP scheduling strategy to meet the objectives. Automating this means doing a search for the best performing scheduling strategies with certain parameters, and this can be supported via standard AI search heuristics like genetic search algorithms. For the above to work, we need to fortify existing approaches of these OpenMP scheduling strategies to make it ready for utilizing AI/ML. And we need to do so in the following ways. Prototyping of control points to guide the training and finding new scheduling strategies. Defining and specifying new OpenMP features. In particular, we need to think about how to define sets and schedules. And finally, we need to think about software tools where humans can have some interaction with this auto-tuning and searching for the best performing scheduling strategies. In the next sections, I will discuss each of these three aspects. In this section, I'll talk about identifying strategies with control points for training, with the strategies categorized in terms of coordinating OpenMP work across processing units and load balancing work across processing units. A processing unit can be a CPU, GPU, FPGA, DPU, so on. I'll first talk about the strategies for a multi-CPU and a single GPU setup. Then I'll talk about strategies in terms of a multi-CPU and multi-GPU setup. Thinking of just one GPU. these plots on the left show a stepwise tuning of an asynchronous version of an all pairs shortest path graph algorithm implemented in OpenMP offload. And what we can see is through progressive tuning of LLVM OpenMP, we can get better performance coming close to the NVHPC compiler. Now, if we look at the application timeline diagrams, we can see how the overlap is happening when we go from the LLVM synchronous version to the asynchronous version. And so this here is just tuning the host device coordination, and we do so across different programming models and OpenMP implementations. More information can be found in this work at SC22's HiPAR 22. Now, more recently, we've focused in on OpenMP plus CUDA, but doing this multi-parameter tuning. And we did specifically a tuning of an intra-CPU and intra-GPU parallelism, and then we also revisited the host device coordinator parameters, and then we did a tuning of the work partitioning across the CPU and GPU. So when we do this for a dot product for this OpenMP plus CUDA version on Summit, we show that compared to the original version without the any optimizations, we get a lot of opportunities of overlap and load balancing here. And so this gives us an 8x speed up. Now, that's a great result, but not really all that surprising. The more interesting thing here is that when we use a floating point dot product, we get a 3.7x speed up over the unoptimized. And this is really a more impactful result because one would think the GPU should be able to run a floating point computation on its own very efficiently. But with careful parameter tuning that involves the CPU as well, the CPU and GPU together can perform much better. You can find more information on this particular result as well as other results in the paper that's to appear here at HIPC 2023. Now, this provides the groundwork for some future auto tuning. Now, let's consider multi-GPU parallelization. Consider a randomized matrix-matrix multiplication using LLVM's OpenMP offload. Here, we employ a dynamic task to multi-GPU scheduling, which was first shown in the paper here. In more recent work, I've tried to minimize the overhead of this dynamic task to multi-GPU scheduling in a similar manner that I did for the multi-core scheduling I showed earlier, all the while optimizing the coordination across the CPU and GPUs. Additionally, I'm trying to use an OpenMP task to GPU scheduling strategy which must inherit many of the aspects of CPU-GPU tuning mentioned in the previous slide. So in doing this, let's look at this plot which shows the tuning of a dynamic fraction of the scheduling strategy, or the inverse of the static fraction. Here on the x-axis, we see it's varied from 0 to 1, and we see on the y-axis is time, so down is good. And so we see that the minima here for a timing for the version without using the bolt runtime, it is around 0.7. And if we do use the bullet runtime, that it goes further. So this is an additional optimization that we use in terms of the coordination, runtime. And so what we can see here is this dash line, which is the baseline, and that's the MPI version using one MPI process per GPU. We can see that using this dynamic task to GPU scheduling is a notably amount better. And so all in all, we see that doing this sort of tuning is very beneficial for this multi-GPU dynamic scheduling. This is just one dynamic multi-GPU scheduling strategy and configuration. What happens when we first generate several different dynamic multi-GPU scheduling strategies using a user-defined scheduling interface in OpenMP, and then find the best performing parameters for each, and finally compare all of them? So there's a paper here showing a few different scheduling strategies and investigation in this way, though I have expanded on this work since then. In particular, we see here on the left a plot for Heat 2D, and it's run with the LLVM OpenMP offload implementation on a node of Summit. It shows timings for these different task to GPU scheduling strategies. Again, down is good. And from this, we see that the static tasking approach with the dynamic fraction of 10% is the best performing. The reasons for this can be seen in this NVIDIA Insight application timeline plot, where we see very few white spaces here on the top for the static tasking. But when we do this more dynamic and half as hard random multi-GPU scheduling, we see a lot more white space, and that is due to both coordination as well as thread idle time. Now, let's talk about the OpenMP features we need to easily generate these new algorithmic strategies with control points via OpenMP, and then tune those strategies. To use AI/ML more easily for OpenMP, we need to augment OpenMP to be higher level and consider node level heterogeneity. In particular, we need to express parallelism for OpenMP in a way that's closely aligned with the language or model that is widely used, specifically a foundation model. We can do so by considering the key principles of parallel algorithm design put forth by literature on parallel computing in the context of MPI. This literature identifies the key steps of parallel algorithm design as first partitioning a problem into tasks, then generating a task dependence graph, then grouping tasks so that communication requirements are minimized, and finally mapping or assigning those tasks to processors, possibly considering a priori information like network topology. You can find some literature in the form of course lecture notes here. Now, to get you, I have worked with Tom Skoglund from LNL on an OpenMP set interface. This set interface provides a mechanism to describe parallelizing computation via OpenMP in consideration of this literature on parallel algorithm design. Specifically, parallelizing computing with OpenMP involves distributing a set of work units across a set of OpenMP devices or threads, following constraints of a set of data dependencies, and optionally using a set of OpenMP associations between work units and or devices. Now, users or a machine can express sets programmatically in OpenMP as shown here. So with this set interface, You can then define a set of chunks or work units in this way here. And you can also define a set of threads or execution units as shown here. In addition, you can define associations between these two sets. For example, a schedule that you want to define yourself. And this can be in the form of a user-defined schedule. Now, to define this kind of schedule, you have to relate a chunk here to a thread here, and this is essentially a pair of a pair here, and an element, which is a thread ID, here. So this is another set, and you can use this for record replay. And so note that this is an on-to relationship where one chunk cannot be associated with two threads. And you can also define this data device affinity or data thread affinity in this way. But here, note that this is not necessarily an on-to relationship. You can also define data to thread or thread to device affinity as a pair of integers. So you can find more information in this technical report here, and we're actively revising and working more on this in the coming months. I'd like to make another point that at a lower level of abstraction is user-defined schedules and multi-GPU parallelization. Now, sets can essentially be transformed down into these OpenMP constructs. And I'm just going to point out two papers on each of these more specific topics and encourage you to look at these for more information on support in OpenMP for multi-GPU parallelism and user-defined schedules. And I'd like to just point out also that both of these topics by themselves are still an ongoing area of interest for the OpenMP specification, but all of this is being done in conjunction with the OpenMP set interface development. Now, I'd like to go into a little bit on how I'm looking at providing a way to exhaustively search for the best performing strategy from the different generated and tuned strategies, all done in the context of the newly proposed OpenMP features I just mentioned. To do so, let me talk a little bit about work I've done within Cocos tools for OpenMP performance tuning. So Cocos is a performance portable programming model which has multiple backends, and OpenMP is one of them. OpenMP is the most commonly used CPU backend, and Cocos can be thought of as an application or user of OpenMP. Cocos Tools provides binary instrumentation and callbacks for each Cocos library function or region. Let's take this Cocos program using the Cocos OpenMP backend underneath. To optimize this Cocos program's OpenMP underneath, we first use this Clang AST rewriter from LLVM to generate the new OpenMP loop given a priori training data and user-defined hints. This code is then augmented with appropriate knobs to adjust control points. With this, Cocos Tools is built, if needed, to identify control points and tune the parameters, if needed, given trading data. Finally, we run the application with the parameters and generate a performance optimization report. This report is fed back in to step 2, and the process starts again. This is part of ongoing auto-tuning efforts of Cocos tools. And this, as well as a much broader showcase of currently developed Cocos tools, is being presented at SC23 as a poster and an extended abstract that you can find here. Now, let me talk about ongoing work for AI-assisted HPC tools for Cocos programs when deployed with a heavily utilized backend, the OpenMP plus CUDA backend. First, I worked with Iowa State this past year to push forward Code Rosetta for LLM-based source code translation, particularly C++ to CUDA source code translation. Code Rosetta uses a very lightweight 0.8 billion parameter encoder-decoder model. The results shown here, gathered by Iowa State, show high compilation accuracy, beating GPT-4 and Gemini Pro. The results also show dominant BLEU and Claude BLEU scores. This was presented at GTC 25, and the latest developments are at coderosetta.com. Of note, recent work on source code translation to OpenMP is opening the door for C++ to Cocos translation. Another development on AI-assisted tools and runtimes for Cocos is that in the Cocos 4.5 release last December, Cocos auto-tuning features via Apex runtime auto-tuning capabilities were released. A positive outcome was a 1.8x speedup for a matrix-matrix multiply on an NVIDIA A100 GPU on Perlmutter, with the results highlighted here on the right. But this included a tuning overhead of about 30%. Most of that overhead comes from searching for the best performing parameter values, and not so much from the Cocos tool's instrumentation and infrastructure. Right now, I and others at Sandia are working in collaboration with Boston University on low overhead profiling for a given CUDA kernel invocation during application execution using on-the-fly machine learning techniques that infer from a small number of profiling metrics a much larger number of profiling metrics using NVIDIA's Nsight Compute and CUPTI. This collaboration has led to a paper currently under review, and I expect to build on this during the upcoming year in the context of Cocos tools Apex runtime auto-tuning to achieve less tuning overhead and faster convergence times. In summary, we first identified a challenge of OpenMP optimization in that it has a large search space, and this becomes very important for scaling MPI plus OpenMP applications. We then showed an opportunity of AI/ML to prune that search space, but one shouldn't just jump into throwing AI/ML at OpenMP. We should use AI/ML to further prune the search space of already existing OpenMP performance optimization strategies. With this, we showed our approach through different aspects, specifically thinking about modern heterogeneous OpenMP applications. The outcomes were twofold. First, we had a reasonably good training set of techniques with control points that showed speedups, and these can be utilized by machine learning. Second, we have new OpenMP features for ease of use by machine learning, and new software tools for ease of management by humans. Future work is to further develop Cocos tools auto-tuning with OpenMP